Since 1957, the leading tactical mobility aircraft of the United States has remained constant. While dozens of variants have been developed for the C-130, the U.S. has not seen a modern, dominant tactical mobility aircraft that has the capabilities necessary to transport critical supplies and personnel into and out of war zones around the world and compete with the C-130. Until now. This is Cerberus-1, the future of aerial mobility for the United States military. Our team, including myself, James Nagengast, as well as our system architect, Bobby Little, and our MBSE leads, Neo Sim and Samuel Landers, have created, under the guidance and supervision of Dr. Elena Garcia, the future of tactical mobility aircraft for the U.S. military. The goal of this project was to develop a new tactical mobility aircraft, Cerberus-1, to transport supplies and personnel to critical warfare sites and hot zones around the world. Although the C-130 and its variants have ruled the battlefield in terms of transportation for the past 67 years, Cerberus-1 aims to improve on the successes and make up for the failures of the prominent historic aircraft. The dozens of C-130 variants provide different industries with aircraft that are developed with specific missions in mind, from tactical mobility to fire and rescue and storm chasing. Unfortunately, as repeatedly brought to the attention of Congress and as published by several verified sources, these C-130 variants often come up short. According to Leslie Wayne with the New York Times, an inability to consistently drop payloads from height or handle inclement weather lead to the C-130 to be a failure for many of its intended missions. The C-130's success is related to its ability to focus on separate missions and to be improved upon with each new variant. But what if these problems were addressed in the first variant of Cerberus-1? With new technologies and processes allowing for better systems engineering that can directly identify and mitigate thermal regulation problems, as well as other pitfalls of the C-130 through MBSE and MDAO, the potential for the Cerberus-1 is extremely promising. Due to the military transportation focus of Cerberus-1, its primary stakeholder is the Air Force Research Lab, or AFRL. As they focus on many of the downsides of the C-130, Cerberus-1 attempts to meet their concerns head-on with new technologies and design considerations. While addressing the concerns of the C-130, the development of Cerberus-1 will also consider the successful aspects of its predecessor as it aims to meet the same level of versatility. Cerberus-1 aims to meet its different missions in a new manner, as its design focuses on modularity, so that it can be fitted to any configuration that is demanded of it. It also aims to do something unprecedented in terms of tactical mobility aircraft, meet the demands of the troops that use it. It will meet the successes of the C-130 while making up for its failures and simultaneously bringing a level of comfort to improve its user experience to make them as efficient as the aircraft they're piloting. While AFRL provided certain desires within the new aircraft, it was important to consider the successful aspects of the C-130. A combination of both aspects, as well as generalized military aircraft considerations, helped to develop a list of 16 customer needs to be met by Cerberus-1, using a quality function deployment. These customer needs were then weighed and used to develop engineering characteristics of the aircraft. The engineering characteristics developed by the QFD were also limited to 16 most important aspects of the aircraft. Overall, these characteristics came to focus on 3 specific topics: size, weight, and operability. These include major aspects of a standard aircraft flight envelope, as well as payload and weight considerations. These major needs will address several aspects of a successful aircraft, such as operable terrain, storage, and fuel efficiency. These targets set the basis for the success of Cerberus-1.
ConOps for Cerberus-1 includes 3 different mission types as shown at the top of the page. The first of the 3 are supply missions, where we provide weapons, medicine, or any goods needed in the field once a request is sent out. This is Cerberus-1's cargo bay in the open/cargo carrier configuration. The second type is a reinforcement call where Cerberus-1 will act as a troop transport. This will have the cargo bay in the passenger configuration. The final scenario is case evac. In this special case, the cargo bay can be in either configuration as long as proper equipment is loaded prior to departure to take care of the wounded. In some cases, speed is of greater importance and Cerberus will launch without changing configurations, generally occurring when the request is incredibly time sensitive and it can save the soldier's life. The diagram also includes communication lines between different parties, travel lines, and requests, which flush out the various parties involved. Some of the parties are satellites for communication, ground troops who put in the requests, medical staff who are there to assist the wounded, and the Cerberus aircraft itself. Moving on to the functional architecture, we break down our mission into 5 main sections. We have landing and preparation, takeoff, cruise, hostile airspace, and unloading at the mission destination. Each category is decomposed further into some of their constituent blocks. Landing and preparation encompasses all pre-flight checks, including fuel, supplying oxygen if applicable, reconfiguring the cargo bay for the given mission, loading of the payload, de-icing the wings, and taxi. Takeoff is more straightforward and involves using a runway of proper length to accelerate and become airborne and increasing to the correct cruising altitude. The next stage is cruise, where the bulk of the mission time takes place. It involves monitoring weather, communicating with mission control, and maintaining the correct heading. Next is hostile airspace, which involves the detection of enemy aircraft and SAM launches, evasive maneuvers, as well as any offensive measures. The final stage is landing and unloading the payload at the mission target. For the functional block diagram, the top level is fairly simple and goes through the main stages of a standard mission. It goes from loading and preparation of the aircraft to takeoff, cruising or traveling to the final destination, entering and navigating hostile airspace, and finally to unloading at the final destination. In this instance, hostile airspace is further broken down in the second level. At the second level of the FBBD, we have 2 scenarios. The first is when Cerberus is targeted by surface-to-air SAM missiles and details the steps that will be taken to detect and survive the encounter, involving launching countermeasures and evasive maneuvers, resulting in successfully avoiding the missile. The second scenario demonstrates the reaction when an unknown aircraft enters nearby airspace. Assuming the aircraft isn't overtly hostile, communication with the aircraft is attempted, as well as informing mission control of the situation. After the aircraft is determined as hostile or friendly, the mission can either be continued, a course change can occur if it's a hostile aircraft to try to avoid it, or Cerberus would prep to engage the enemy. The engagement with the enemy is further looked at in the third level of the FBBD. For the third level of the FBBD, engaging the enemy aircraft is decomposed into a linear process of events that goes through the stages of combat. The first block assumes there is enough time to secure on-flight personnel before engaging the enemy. Cerberus often operates with an armed escort, as it is primarily a transport aircraft, but due to military advancements, it can still assist in aerial combat and help the escort if the need arises. After destroying the enemy aircraft with a lock-on missile or the onboard guns, Cerberus and the escort can return to standard mission procedures and resume the top-level FBB diagram to resume course to the final destination.
Our requirements were heavily based on the current capabilities of the C-130. As James explained earlier, we want to surpass the capabilities of the C-130 and not just simply meet them. We plan to accomplish this by taking advantage of technological developments that have come out since the C-130 was designed. With these requirements, Cerberus 1 will be more compact than the C-130 with a shorter wingspan. It will also perform better with a higher maximum payload, range, speed, and operable ceiling. Cerberus 1 will also have a lower empty weight, which allows for more of the total weight to be allocated to payload specifically. All of these requirements were documented and organized using model-based systems engineering, also known as an MBSE model. When it came to ranking the metrics for these requirements, the team had to agree on a set of criteria that reflected the overall project's goals. We decided that we wanted Cerberus 1 to be the best tactical mobility aircraft for years to come, prioritizing performance and the meeting of mission needs over the physical size or cost considerations. As an aircraft that will be heavily used for transportation of troops or cargo, we decided to prioritize weight-related requirements as well as range at the top. This would ensure that Cerberus 1 will prioritize transporting the largest payloads the furthest distance. While at the bottom, requirements like physical length of the wingspan and mean time before failure of components were ranked lower. Mean time before failure was considered a cost-related metric, as with enough investment, we reasoned that parts and maintainers can always be on hand to regularly replace aircraft components. Investment in Cerberus 1 will be high, but it will be a best-of-its-kind aircraft for years to come. Within our MBSE model, we also created a parametric diagram to investigate two different configurations of the aircraft. Our goal was to investigate how the weight allocation of each subsystem would change under two different configurations. The first configuration was designed to maximize range at the expense of payload, while the second configuration was designed to maximize payload at the expense of range. The range-optimized configuration took up much more weight for components like engines and fuel. The range was maximized by utilizing 4 smaller engines with larger fuel storages, which meant less of the overall weight allocation was able to go to payload. The payload-optimized configuration gave a much higher allocation to payload while reducing fuel storages. It also implemented 2 larger engines that overall weigh less than the 4 smaller engines. However, the larger engines could produce more thrust per engine to accommodate the larger payload. Case 2 did a better job of meeting the needs of a tactical mobility aircraft to be able to carry more cargo, so we decided to further develop this concept. In order to compare some possible alternatives to various critical aircraft components, we created a morphological matrix. The team came together and brainstormed some possible alternatives to the list of subsystems shown here. Ultimately, it was decided that this set of options highlighted green would work well for Cerberus 1. These selections give Cerberus 1 a good balance of high-tech subsystems like advanced stealth capabilities against tried-and-true subsystems like a fuel-based turbofan engine. The key here was finding elements of the aircraft that would best suit its needs while being realistic about the technological readiness of each component, which influences how soon and how effectively the technology can be implemented with Cerberus 1. With these components, we will be able to give customers a cutting-edge aircraft that will still perform reliably.
All right. The propulsion system is one of the most critical and expensive components of the Cerberus 1 aircraft, making it the logical focus for our first trade study. Using the TOPSIS method, we evaluated 5 engine options against key criteria such as thrust, cost, specific fuel consumption, weight, and noise level. This rigorous analysis provided a clear ranking of alternatives. As shown here, the Pratt & Whitney PW4000 emerged as the optimal choice, offering the best balance of performance and cost effectiveness. This decision ensures that Cerberus 1 meets its operational requirement while staying within budget. Our comprehensive analysis and trade studies have culminated in this initial conceptual design for Cerberus 1. It's a modern tactical mobility aircraft that blends innovative aerodynamic efficiency, modular payload capability, and advanced propulsion technology. This design ensures that the aircraft will excel in diverse mission profiles, from high-altitude surveillance to rapid supply delivery. This is not just a vision. It's a practical, achievable design backed by robust engineering and analysis. Ensuring compliance with size and operational requirements is a cornerstone of the Cerberus 1 project. Here you can see how we plan to verify each critical requirement using methods such as inspection, testing, demonstration, and computational analysis. For example, runway performance will be validated through controlled landing tests, while structural analysis will ensure the aircraft meets maximum payload specifications. Every requirement is paired with a clear verification method and the necessary support equipment, leaving no room for uncertainty in performance validation. Every ambitious project comes with risks, and Cerberus 1 is no exception. We've conducted a thorough risk assessment identifying potential challenges across design, operations, and supply chain management. Each risk is categorized and matched with targeted mitigation strategies. For example, supply chain delays are addressed by diversifying suppliers and maintaining inventory reserves, while defense system failures are mitigated through robust redundancy and rigorous testing. This proactive approach minimizes uncertainties and ensures project success. This risk matrix provides a visual summary of the likelihood and severity of each identified risk. As you can see, our most critical risks, such as exceeding budget or supply chain disruptions, fall in the red zone, and we've prioritized them accordingly. By focusing on these high priority risks and implementing our mitigation strategies, we can confidently steer the Cerberus 1 project towards successful completion. All right, to conclude, the groundwork has been laid for the next generation of tactical mobility aircraft. Cerberus 1 is designed not just to meet, but to exceed the operational demands of today and tomorrow. Its versatility and adaptability make it the ideal candidate to support a wide range of missions ensuring superiority on the battlefield. With your support, we can bring this groundbreaking platform to life, providing our forces with the tactical edge they deserve. Thank you and have a great day.